this was a good idea, and the idea was that if function is sensitive, then you have to look at all these log n plus 1 things, right? Let's look at another function. This is called threshold 2. This is one if and only if there are at least 2 ones okay, this is not a good idea, but what do I want to do? Not threshold. Two consecutive ones. Okay, so if all these are 1, if there are 2 consecutive ones, I find exactly 2 consecutive ones, I give 1, otherwise 0. Correct? Now, if you think about it, look at the input 0, 0, 0, 0. Correct? I have to query something from first 2 for sure. Because if you are not querying from here, I can switch both of these to 1 and get the function value 1. Similar argument, I have to query from this, I have to query from this, I have to query from this. So I have to make at least intuitively, right? Here, there is not one bit is sensitive, but instead I have to change a block of 2 values, and the function value switches. What I am saying is still the same arguments can be applied. That is extra. I don't need that. I am proving a lower, but I am saying even if you don't consider that input, even then you will have to make n by 2 queries. At least n by 2 queries. Okay. So remember, like in the OR case, there are 2 to the power n inputs, but for proving a lower bound, we only looked at n plus 1 inputs. I am now looking at n by 2 plus 1 inputs. What are the inputs? Okay, and again I am saying, your algorithm keeps asking me what is the value of y1, what is the value of y2. I will keep answering 0, 0, 0, 0. You mean here? Then what I want to say is that you have to do at least one query from all of these. If you take 0, 1, 1, 0, 0, 0, 0, then I can settle both of these just with one query. So places where I am flipping, I want these blocks to be disjoint. If I query from here, that doesn't mean I have queried from this block. See, okay. I tell you that you have to query from here, you have to query from here, you have to query from here. I want to say that means you have to query at n by 2 places. That will only be true if querying here does not affect the thing here. Like one query cannot settle both, right? If one query can settle both, then I really don't need n by 2 queries. If this was also your input, this and this, potentially asking y2 can settle both, no? Not just second bit. If the second bit is 0, I know that this is the answer, this is not the answer. Right? There is a common bit between these two. So querying second bit here also is telling me something about this input, this input. So then I will not be able to say that you definitely have to query distinctly from all these. That is why I need these blocks to be disjoint. Okay, so this lets me define the measure called block sensitivity. Okay, so I am making my lower bound stronger and stronger. I was saying that, oh, how many bits are sensitive? Instead, I am saying, suppose I have blocks which are sensitive. Even then, I can prove a lower bound. Okay, notice in this case, the sensitivity is small. What is the sensitivity at all 0? 0. Right? Correct? Okay. What is the sensitivity at single one? Just 2. You can either flip the one afterwards or one before that. Right? But this input, because you are allowed blocks, you can show a bound of n by 2. Okay. So then what you do is you say that even if you look at x, you have these k disjoint blocks. It is important, right? This is the question which Divyansh had in mind. These should not share any indices. Okay, so now B1 is first 2 bits, B2 is third and fourth bits, Bn by 2 is last 2 bits. Anytime you switch bits from Bi, your function value switches. And then the idea would be that you have to query from each block. And again, we will define and this clearly block sensitivity is bigger than sensitivity, because I can take blocks to be of size 1, that will give me sensitivity. Almost the same proofs give you this. Only if 2 consecutive blocks are 1, then no. Blocks need not be consecutive. Like B1 could have first index and nth index. It doesn't matter, right? This whether they are consecutive or not does not matter. The point is that switching those switches the function value, right? Consecutive did not help anywhere in this argument. Yes. So that I did not say. In some sense, this is the maximal partition for which, yeah, very true. Did not go into detail because I will not go into block sensitivity, but you are completely right that there are many such disjoint block sets. Among them, you pick the maximum. That will be block sensitivity of f of x. Then you maximize over. Right? Yes. Right. So, for example, the same thing here. I can take this. Yes. So if I want threshold 2, okay, so me answer. What is threshold 2? At least 2 ones in the input. Okay. Now look at all zeros. Block sensitivity n by 2. That answers your question, Shwesh, right? So this partition also shows block sensitivity is n by 2. You can use that also in threshold 2. You have many such choices. Maximum is n by 2. Yes. Yeah, so number of blocks, huh? No, that partition did not answer Suesh's question. He wanted blocks which were not consecutive. So if block says I1, I2, I2 should not be I1 plus 1. The 2 bits which I am flipping, they need not be consecutive. No, they can be of different size. Yes. No constraint. They have to be some blocks. Cool. Now, the picture, remember, what was our target? We want to look at df and qf, and we want to bound df by qf to the power 4. So, actually, the picture looks like this, and square root of sensitivity, or you can say block sensitivity, right? So df is bigger than block sensitivity is bigger than sensitivity. You can even put RF. Again, some of these I am not proving, so this needs to be proved, but this we have proved, this we know, this we know, this we know. Okay. Again, in the sense that whatever we did for optimality of Grover search, the same arguments can be extended to these lower bounds. Okay. Cool. Now, I will introduce another quantity. So sorry, I should not write it here. I will use another quantity, and I will show that this is also a lower bound on degree, and something related is a lower bound on Q. Again, this final result, df is bounded by Q to the power 4, will result from interplay between all these quantities. And there are a lot more, but I am only introducing the ones which we need. Okay, so yeah, be patient. Again, remember the reason. We want to prove df is less than qf to the power 4. Okay. So all this is trying to understand how complex a function is, right? You have a function 0, 1 to the power n to 0, 1, how complicated it is. If quantumly you need one query, then the function is probably simple quantumly. If you take root n queries, then function is kind of difficult. If you take order n queries quantumly, then it is really, really difficult. Correct? But this difficulty, you can say in terms of quantum computation, in terms of deterministic computation, in terms of randomized computation. Also in terms of sensitivity. If the sensitivity is small, function is less complex. If the sensitivity is more, function is more complex. So now we study these complexity measures. Another complexity measure will come from your favorite polynomials. a function which can be represented by a linear polynomial, degree 1 polynomial, is that more complex, or it can be represented by degree 2 polynomials? Which one is more complex? If the degree becomes higher, then the function becomes complex. Correct? So what we are going to do now is going to represent these functions as real polynomials. And the degree of that real polynomial is going to be the complexity measure for f. Okay? So we want to represent our functions as polynomial. How successful have we been in representing functions as polynomials? Can all functions be represented as polynomials? No, not all Boolean functions. General functions like sin x, cos x, you can't represent them as polynomials, right? They are represented as power series, not polynomials. Correct? You can't say their degree is finite or something, right? So, but this space is going to be very, very nice. Every function I will represent using polynomial. Okay? And I will prove it very soon. Once again, simple high school mathematics. So now, this is the truth table of the function, right? Given f, I have to the power n entries here. Okay, let's take the simple function, which is 1 here and 0 everywhere else. Can you write this as a polynomial? What is the polynomial? For this function which takes value 1 at all zeros and 0 everywhere else. And is not a polynomial operation, but right, this will only be 1 if everything is 0, otherwise it will be 0. Correct? Let's change this slightly. What is the polynomial? Sorry? Sure. Okay. So now, can you tell me for a general function what is the polynomial? Okay. I will give you a hint. What about this function? What is the polynomial here? Sorry, x1, x2. Why did you omit x1 part? Okay, okay, you are right, but I am looking for something else, so I will keep moving on. Yes, Sahib. Exactly, not addition modulo 2. I will add. This is a real polynomials. Just add. What do I know? This is 0 everywhere except here. This is 0 everywhere except here. If I add this, when will I get 1? Only if both of the, at least one of them is 1. Can both of them be 1? No, right? So this will be you see how x1 disappeared? Correct? right? Yes, no, questions? Yes. So now that means given arbitrary ones here, I can take the corresponding polynomials and sum them up. These are called indicator polynomials. Sorry? Oh, what happened here? Oh, I'm saying I'm trying to construct polynomials for every function. So first I take these simple functions which are just one at one place. Can you create polynomials for them? Yes. Now if there are 3 ones, I will just add these indicator polynomials at these 3 places. They will become polynomial for this function, because what will happen here? This one will become 1, rest 2 are 0. What will happen here? This one will be 0, this one will be 1, this one will be 0, again I get 1. Everywhere else, this will be 0, this will be 0, this will be 0. Here, this will be 1, 0, 0, I am fine, right? So what I have shown is, if there are k ones, just write your polynomial as sum of those k indicator polynomials, right? So every function of this kind can be written as a real polynomial. Okay, and we also know that the degree of that polynomial is less than, what is the degree here? N, at most n. If you sum up n degree polynomials, it will be at most n. There can be cancellations, so it can go below n, but degree is always less than n. These polynomials will represent the function on these inputs. I don't care outside this range. Like what happens when I put x1 equal to 2, I don't care. I only care at these 2 to the power n points. Okay? Sounds good? You can also show that every function has a unique polynomial of degree less than equal to n. Okay, and I give this as an exercise. Every function, I showed that there is a polynomial representing it of degree less than n. So if you restrict yourself to degree less than n, there is exactly one polynomial which represents it. And the proof basically would be, if there are 2 polynomial representations, you take their difference. So then, now I have a polynomial which is 0 on all 2 to the power n values. You can show that cannot happen. You have a polynomial which is not 0, which has degree less than n, it cannot be 0 on all n 2 to the power n values. This, I leave it as an exercise. But this is showing that f has a unique polynomial of degree less than equal to n representing it, say Pf, and I define the complexity of f to be degree of Pf. And what you can show, again which I haven't shown, is that df is bigger than degree of f. So, okay, you are with me, right? Now, ideally, we want QF to be bigger than degree, right? That would be great. Like, I had sensitivity, block sensitivity. This was a lower bound on D, but I found something which is related to this, which was a bound on Q. Okay. What is the degree of OR function? What is the polynomial representing OR? x1, x2, xn? No, sorry. Yeah, go ahead. What is the polynomial representing OR? Summation of 1 minus xi. No. Okay. What is the representation for this? Correct, this we have done. What is OR? Correct. So what is the degree of OR? N. Correct. Can degree be a lower bound on QF? No, unfortunately. Right? Because Q of f is root n, Q of OR is root n, degree of OR is n. So I know a function where this is not a lower bound on this. So degree of f cannot be a lower bound on QF. If it is not true for one function, it cannot be true for all functions. Right? So what happens is, there is another measure which is called approximate degree, which is a lower bound on QF. Because for OR, degree cannot be a lower bound on Q. For OR, Q is root n, this is n. So degree cannot be a lower bound on Q. So now we are asking, by similar proof techniques, can we come up with a polynomial complexity measure which is a lower bound on Q? If you do this, you will get this thing called approximate degree, and this is kind of intuitive. What does approximate degree say? The polynomial does not give you the exact value 1 or 0, but it is close to 1 or 0. When you compute quantumly and randomly, you don't get the probability to be exactly 1. You get the probability to be close to 1. Right? This is what you do here. You say that your polynomial need not give you the exact value at x. So now P represents f if this 1 by 3 is the same error probability which we used for the quantum algorithm. Okay. So now if you define your degree by the degree of this polynomial, so there are a lot of polynomials which can represent f, you take the minimum possible degree, that becomes a lower bound on Q. Again, a lot of things I have not shown, but I don't have, but again, the idea is you looked at D, you created measures which were a lower bound on Q. You looked at D, you found a measure which was a lower bound, similar measure becomes a lower bound on Q. Okay? Sorry? We have a polynomial. No, we don't have degree. We have approximate degree, yes. Yes, approximate degree, yes. These are called Chebyshev polynomials. You can look at them. I can show you after the class, not here. Okay. So there are polynomials which are close to the value of OR at every point, but their degree is very, very small. But you can take my course next semester. I will cover that. That's the motivation. Okay. So all these questions I will answer in the next course. Unfortunately, I don't have time in this course to answer these. Okay. Right? Sorry? This is more absolute value. This is not norm. Absolute value. this is a real number, this is a real number. I am taking their minus. So basically, if f of x is 1, then p is between 2 by 3 and 4 by 3. Polynomial, a polynomial. Like the polynomials which you wrote, right? Yes, real coefficients. It's a real polynomial. Yes. So the proof that approximate degree is bigger than square root degree was proved 2 years back, which was an extension of Huang's result, which I will be proving. Yes. So yes. So you can say that square root of degree is a lower bound on QF. Like square root of BS is a lower bound, square root of degree is a lower bound on Q is a result which is only 2 years old, 3 probably, which is actually an implication of the Huang's result, which I will show you. So this is very, very interesting. Okay. So simple questions, analogous questions have been very, very difficult. Like sensitivity is a lower bound DF, square root sensitivity is a lower bound on QF. Degree is a lower bound on DF. Is square root of degree a lower bound on QF? Very, very recent result. Okay, 2021. So recent. yeah. You know, I'm old, so I'm always in 2020s. All years are same for me in 2020s. Okay, recent. Right. So now I can tell you how we are going to approach. So one of the major and not very difficult part is to prove this. Okay. Remember, what do we want to show? In some sense, we want to show that DF is small, QF is big. If we want to show that DF is bounded by QF to the power 4, in some sense we are making this interplay. We want to reduce DF, we want to prove upper bounds on DF, we want to give lower bounds on Q. Okay. So this will be the upper bound. Okay. Now, block sensitivity is bounded by QF square. This is something which I will not prove, but this is true. Okay. And I just told you that square root of degree is a lower bound on QF. So then there will be a QF square here. Okay. So this is Huang's result. And this result was like 1993 or something. That's why I'm saying that almost everything was known 30 years back, and then there were 30 more years to kind of prove the remaining things. Okay. So next class we will do degree lambda f square, where this was known before. So we will introduce another measure. We will show degree is bounded by lambda f square, which will turn out to be degree is bounded QF square. So both these quantities are bounded by QF square, QF to the power 4. And if you are interested in this proof or this proof, this is just a generalization, so I won't even worry about it. This is also a generalization. DF more than degree, all these are given in notes. Okay. So from notes, you have all the proofs which I am missing here. If you are interested, you can go and read those proofs. Unfortunately, I don't have time, but yeah, but all those proofs are there. Using that also, because then you can get that degree of f is bounded by approximate degree f square, then QF. But this proof itself uses this proof. Yes, so this was the recent result on which people built up and proved. So this was 19, like 2019, and this was 2021 or something. So I will cover this result, this. And this result is nice because what it showed for the first time was that you look at all these measures, these are all polynomially related. None of them can be exponentially away. So this was a question for a long time. You have this zoo of complexity measures, algebra, combinatorics, computation. Look at all these complexity measures, how far away can they be? Can they be exponentially far away? Most of them could not be. This showed none of them could be exponentially far away. That's why this was a big result. This was open for, as I said, okay? This is also in the notes. I was planning to cover it, but already I'm out of time. Okay? So this is the outline, the main recent result we will cover in the next class. Cool?